Okay. Where did we leave off? We did some examples with the fundamental theorem of calculus part 2. So what's the fundamental theorem part 1? We'll introduce it with this example. Let's call g of x the function where we're looking at the definite integral from 3 to x of 2t dt. Now that's definitely a strange way, like a new way of creating a function. We're saying the variable is the upper limit of integration. So, if we wanted to know g of 10, then we would make 10 that upper limit. We'd be taking the definite integral from 3 to 10 of 2t dt. And, as we change x, it's like we're changing that b value, and obviously the area between the function and the x-axis would change. Okay, all right. We're asked to find g prime of x. So here's what we'll do. We're going to work through all the steps to finding g prime x, taking the antiderivative and all that. And when we get done, maybe we'll notice that, we could have gotten to this answer a lot faster when we reflect on it. Okay. So if g of x is the definite integral from 3 to x 2t dt, what should we do to start? We should take the antiderivative of 2t. So we know that the antiderivative of 2t, right, is t squared. And then we will evaluate that from 3 to x, right? If we plug those in, starting with x, right, we plug x in and get x squared. Then we'd subtract, plug 3 in and get 9. So we would realize, wow, g of x is really just x squared minus 9 in disguise, disguised as that definite integral. That's interesting. Okay, but the point is we have g of x just as a regular everyday function now. So what's g prime of x? Well, I'd take the derivative of that and we'd get 2x. Okay, so let's reflect what happened here. Notice that we started with 2t dt inside that integral. G prime of x ended up being 2x. Coincidence? No, definitely not. Think about it, right? So we took an antiderivative, and then we took a derivative, and they canceled each other out. Antiderivative, derivative. Now we had to create a new variable. We had to create this t variable because we already had x here, and there was going to be an integral. And so the variable changed from t to x, but it's still the same. It's still 2 times the variable, whatever that was. Also notice, because the 3 in the bottom, we plugged the 3 in, but the derivative of that minus 9 was 0. So it turned out, did it even matter that that was 3? Could it have been some other number? Could it have been 4? Could it have been 0? Could it have been 1? Could it have been negative? Didn't matter what this number down here was, because after plugging in and taking a derivative, it's just going to go to 0. Okay, interesting. So this is the fundamental theorem of calculus part 1. Now, what does the fundamental theorem of calculus do? It connects integrals with derivatives, and it shows us that derivatives and integrals are opposites. If you want to find the integral of something, then you need the antiderivative. Okay. So our textbook considers this as the starting point, and then it goes on to do part 2, but I think it's way more interesting and way more fun to do in the reverse. So okay, what does this say? If f of t is continuous on the integral from a to x, and g of x is defined as the definite integral from a to x, f of t dt, then the derivative of g of x is equal to f of x. All right. So what we're saying is, right, our f of t, that was our 2t here. If we want the derivative of g, the derivative is simply going to cancel out the integral. And it's going to give us that function here. It's like do a derivative both sides. Well, this derivative on the right side cancels the integral. And we end up with f of x just because of the nature of the way the variables change. Okay. How is this like helpful or interesting? It is helpful and interesting. The applications of the fundamental theorem part 1 are really few and far between. The fundamental theorem part 2, that's what we want. That's what we're going to use in future sections. We are only going to see the fundamental theorem of calculus part 1 in this section. And we need to note it because it does come up, again, very few and far between in the future. On that note, from here, after this section and out, if we say just the fundamental theorem of calculus, we mean part 2, capital F of B minus capital F of A. But we definitely need to mention part 1 here. Okay, so we're going to do a few examples with this. We're going to kind of like mix things up a little bit, have some fun with it. We're going to take a look at these. We're asked to find the derivative g prime of x. Notice the first 3 examples we'll look at are very similar. So we'll look at, we're going to, increase the complexity a little bit and look at square root t cubed minus 1. In part B, we're going to switch the order of the integrals. In part C, we're going to change x to x squared. Oh man, okay. And then in part D, we're really going to change things up and throw in sine x. And okay, let's check this out. Find g prime of x. Part A. We're told that g of x integral from 1 to x square root t cubed minus 1 dt. All right, now that we know the fundamental theorem part 1, we can just go immediately to our answer. What is g prime of x? Hey, here's f of t. So all we're going to do is repeat that, but put an x in place of the t, and we got it. No work at all, since we know this theorem that integrals and derivatives cancel each other out. Okay, before we go into part B, let's just kind of like pause and kind of like reflect on what we just did. So we skipped all those middle steps, right? Here's the thing. For this particular function, square root t cubed minus 1, we wouldn't be able to do those middle steps even if we wanted to, right? Like the example we did earlier with 2t, we could do the antiderivative, plug in the x, plug in the 3, do a derivative, right? We could do it that way. Here, you're right, good luck. What is the antiderivative of square root t cubed minus 1? What do you take the derivative of to end up with this as your derivative? I don't know. I have no idea, right? There'd be like a chain rule, right? If you thought of it as t cubed minus 1 to the half, you think, well, this must have been like to the 3 halves, but then there's a chain rule, and would we have just had to like divide by 3t squared because that's, well, no, because it couldn't have been this function because that would require a quotient rule. That wouldn't end up with that, so, or like, with the 1/2 or something, or excuse me, 2/3. Because that would multiply down and then drop to 1/2, and then you multiply by 3t squared, but that wouldn't work because that would require a quotient rule in your derivative. It wouldn't just be a matter of canceling. Yeah, okay, anyway. The point is, we don't know We don't know what that antiderivative would be. But whatever it was, some function, it'd be something, but we just don't. Whatever it was, we'd plug x into it, we'd subtract, we'd plug the 1 into it. When we plugged in the 1, it would just be a number. Then, because we're trying to find g prime, we'd take the derivative. Well, the part that we plugged x in, the derivative would just go back to this. The part that we plugged in the 1, that derivative would go to 0, and there we go, we got it. So I don't know what the middle steps are, but whatever they are, it would have to result in this for our derivative g prime. Fascinating. Okay, let's try this again. This time though, we're going to switch the order of the x and the 1. We're going to put the x on bottom, the 1 on top. G prime x. G prime x. Hey, there's a property of integrals on this sort of thing. That property said if they get switched, it's the negative. And so this would be negative square root x cubed minus 1. You know, one way to think of it is, well, we could switch it back and then put a negative out front and then use the fundamental theorem part 1 and then get this part, and there's just that negative carries along. That would work. Another way to think about it would be like that kind of like slightly mystical kind of a way where we don't know the middle steps, right? If we were to get that antiderivative, which would be the same one, right? Whatever it is, this time we'd plug the 1 in first. It would create just a number, subtract, plug in the x, then take the derivative. The part with the 1 plugged in would go to 0. The part with the x plugged in would go to this, but it would have been subtracted. So there we go. Part C. This one's fun. Okay, back to this order, but let's make it x squared. Really interesting. Okay, this is what we're going to do. It begins with taking the x squared and putting that in for t. X squared cubed minus 1, like so. That's what you were thinking. So far, so good. But it turns out we're not done. There's something else we need to do. Turns out we need to multiply all of this by something. What should we multiply all of it by? And if you kind of look here, you're thinking, the x squared is inside parentheses. There's an inside-outside going on with this derivative. We don't know what the outside function was, but we do know that x squared was inside of that, where all the x's were. So we're going to have to apply a chain rule. The derivative of the outside, whatever the thing was, came out with this, but now we got to multiply by the derivative of the 2x. So, or excuse me, the x squared. So there's the 2x. And maybe we should write our final answer this way: 2x square root x to the 6th minus 1. Simplify it up a little bit. Where did that 2x come from again? This accounts for the chain rule on the x squared. All right, we got one more. Here it is, g of x equals definite integral from sine x to 4 t e to the t dt. Oh, yes. Okay, what do we notice? Couple things. We've got sine x, right? So we're going to need to do a chain rule. Also, the sine x is in the lower limit of integration. So that means we're going to have to use a subtraction in front. So we got this. Check it out. Negative. Now, oh, it's kind of a third element. We have t appearing twice. Sine x goes in for both of them. Negative sine x, e to the sine x. Then account for the chain rule on sine x, cosine x, and that's it. You might be thinking, hey, since it appears twice, do we do the chain rule twice? No, the chain rule applies only one time to the sine x derivative. There it is. And maybe our final answer, we can put that cos x out in front like so. There it is. We got it. Well, everyone, that is it for the fundamental theorem of calculus. Hope you enjoyed. See you next time.